Hi, today I will talk about our recent work on compiling graph applications for GPUs with GraphIt. This work was done jointly with my collaborators from CSAIL MIT and Adobe Research. Graph and graph applications power almost everything around us, including recommendation and search engines, map searches, and fraud detection. The quality of service of these applications depend a lot on their performance, and hence it is critical to choose the right set of optimizations when implementing them. The exact choice of optimization depends not only on the algorithm to run, but also on the variations in the graph input. Real-world graphs used in these applications have very different vertex and edge distributions. For example, we typically see power law degree distribution in graph depicting social networks. Road networks used in maps, on the other hand, typically have bounded degree distributions. Similarly, the algorithms commonly used also have different features. For example, PageRank is an example of a topology-driven algorithm where each vertex is processed every round. Shortest path, on the other hand, is an example of a data-driven algorithm where only a subset of the vertices are processed every round. Each combination of these algorithms and graph requires different optimizations. To navigate this vast space of optimizations, we previously built the GraphIt domain-specific language and the compiler. The key features of GraphIt is that it separates the algorithm representation from the schedule. The programmer writes in an algorithm language what to compute. The programmer also writes a schedule in the scheduling language, which is how to compute. Both of these are then fed into a specialized compiler that generates high-performance C++ code to run on CPUs. The developer can then change the schedule slightly to generate entirely different implementations with completely different optimizations. The GraphIt algorithm language is an imperative language with data structures and operators tailored to the graph domain. We have data structures like the edge set, which is used to hold the actual graphs to operate on. We also have the vertex sets, which hold a subset of the vertices to be processed in each round. For example, in applications like breadth-first search. These data structures are abstract in the sense that the algorithm language and the operations to be performed on these data structures are independent of the underlying representation. The edge set can be represented as CSR, COO, block CSR, and so on. Similarly, the vertex set can be represented as a bitmap, bool map, or a compressed sparse queue. The compiler chooses the appropriate representation based on the optimizations applied. GraphIt also has support for a priority queue data structure to support processing vertices in a fixed order either for correctness or optimization. GraphIt also has operators or primitives like the vertex set.apply or edge set.apply, which, as their name suggests, allows applying some function or operation to each vertex or edge in a set respectively. Just like the data structures, these operations are also abstract, and their actual implementation is generated by the compiler based on the optimizations applied. Finally, GraphIt language allows the user to write user-defined functions or UDFs to specify the actual computation to be performed on each vertex or edge. These UDFs are transformed heavily by the compiler to fit the call site and optimizations. We will discuss some of these transformations in the talk ahead. For the optimizations, the user can annotate these operations with tags like shown between the pound sign. These tags can be then referenced in the scheduling language. The scheduling language is embedded in C++ and allows the programmer to call functions to configure parallelization, direction of iteration, cache and NUMA optimization, among many others. The algorithm language is first passed by the compiler to produce an internal AST or abstract syntax tree representation. A variety of analysis, transformation, and lowering passes are invoked on this AST depending on the scheduling input given by the user to produce a final AST which is then sent for code generation. Unlike the other library frameworks, the Graph DSL compiler is able to perform whole program analysis and transformation, which makes it easy to combine optimizations, resulting in a wider scheduling space. This wider scheduling space allows the user to choose the optimization that best suits the variation in their application and graph inputs. Another variation that is typically encountered in this application domain is variation in hardware features. For example, when running a topology-driven algorithm like PageRank on social graphs, all edges originating out of every vertex in the graph is processed every round. These kind of applications have massive amount of parallelism, often access memory in a coalesced manner, and have a regular work distribution, and are thus well suited to run on GPUs. On the other hand, applications like single source shortest path when running on road graphs process very few vertices and edges each round, offering very little parallelism and are thus well suited for running on CPUs. Unfortunately, when exploring these variations, the developer has to rewrite the implementation in an entirely new language using completely different abstractions like CUDA. Even within the GPU space, there is a plethora of optimizations, and applying each manually and writing the complete implementation is time and effort consuming. There is currently a lack of a single framework that can generate the code for both CPUs and GPUs from a single input. Ideally, we would want to take the same algorithm input as Graphit, provide a GPU schedule, and generate high-performance CUDA that can be run on GPUs. To achieve exactly this, we built G2, the GPU extensions to the Graphit compiler. We will now go over different parts of the G2 compiler shown here to see how all of them work together to get the best performance for the code generated on GPUs. As mentioned before, G2 uses the same algorithm input as Graphit, thus requiring the developer to write the algorithm specification only once. G2 then adds a GPU-specific scheduling language tailored to optimizations on the GPUs. Our experiments have shown that the optimization space of GPUs is much larger than that of CPUs. Hence, the GPU scheduling language is richer in choices it exposes to the user. While generating code for GPUs, the user has to answer a lot of questions, like whether the code will use direction optimization, whether it will use kernel fusion, whether it will block the edges for cache optimization, what kind of load balance strategy will be used, what kind of data representation will be used, and so on. We identified the following 6 key decisions that are critical for performance on GPUs and exposed them to the user in the scheduling language to the functions on the right. We also show the comparison of available features with 3 other state-of-the-art graph processing frameworks for GPUs, namely Gunrock, GSwitch, and SepGraph. We can see that G2 supports an order of magnitude greater number of combinations of optimizations in the code that it can generate. This is mainly because of the rich scheduling language and the ability of G2 to combine optimizations using the compiler. Let us see how G2 is able to achieve this massive feat. The bulk of optimizations in G2 are in the midend phase. The midend is a series of analysis and transformation passes running on the algorithm representation before code generation in the backend. These passes are parameterized by the scheduling language input for both correctness and performance. Let us look at one such pass in detail. Here is an excerpt from a typical G2 algorithm input with a user-defined function update edge that is applied to each edge being processed. This function has a sum reduction in the property IDs associated with each vertex. When invoked in parallel, this reduction might require atomic synchronization for correctness. To keep the developer effort at minimum and not requiring them to manually insert atomic synchronization, the G2 compiler performs a data flow analysis to identify shared and independent variables in the user-defined function. Let us zoom into the function and see how it works. We will track the shared and independent values in the user-defined function in each step. For the first case, we will specify a schedule that uses the push iteration where we iterate over the sources of the edges and push the values to the destination. We will also use a vertex-based load balance where each vertex is iterated on by a single thread. It is easy to see that the destination value will be shared among the threads, meaning 2 threads can have the same value for the DST variable. This is because 2 different vertices in the graph can have the same neighbor. The sources, on the other hand, will be independent because each vertex is assigned to a single thread. On propagating this information, we can see that the vertex property of a shared value is being updated, and hence G2 inserts appropriate atomic synchronization here. For the second case, let us look at a schedule that uses the pull iteration, where we iterate over the destinations and pull the value from the sources. We will again use the vertex-based load balance. In this case, the destination will be an independent value and the source will be a shared value. On propagating the information, we can see that the vertex property of an independent value is being updated. This means that two threads will never conflict in the memory location they update. So the compiler does not insert atomics here to avoid the performance overhead. Finally, let us look at another case where we use a push iteration and TWC load balance, where the edges from a single vertex can be assigned to multiple threads. In this case, both the source and destination are shared values, and the compiler inserts atomic synchronization for the update to preserve correctness. The Midend optimizations has transformation and analysis that are common to both CPUs and GPUs. The GPU backend, on the other hand, has all the GPU-specific analyses and transformation, a CUDA code generator, and a runtime library for running on GPUs. Let us look at an example of a GPU-specific analysis and a transformation. Here is a typical host-side code for an application like BFS containing a while loop. On the right, we show the naively generated code for this loop. We can see that the code allocates and deallocates memory for the vertex set variable each iteration. But these calls to CUDA malloc and CUDA free are very expensive, unlike on CPUs. But if we look at the code carefully, we can see that we don't need to allocate and free the memory every round. We can simply reuse the memory allocated for the variable frontier to be used by the variable output. But before the compiler can automatically do this optimization, it has to figure out whether it is safe to do so. Mainly, it has to answer if the input vertex set can be used again. The compiler uses a classic liveness analysis to figure this out. We will create the live ranges of all the variables of the type vertex subset inside the while loop. On doing so, we can see that the variable frontier and output have disjoint live ranges, and thus the compiler can conclude that they can reuse the allocated memory. Next, let us look at the Kernel Fusion optimization that is implemented using a combination of transformation and code generation passes. Recollect the example of single short shortest path running on road graphs. We remember that very few vertices are processed each round, but we have to launch a separate CUDA kernel for each iteration to perform very little work. This leads to a problem that the kernel launch overheads start dominating the execution time. We can get around this overhead by launching a single CUDA kernel for the entire while loop. But before we do that automatically in the compiler, we have to determine if the transformation is valid and how the code would have to be changed to implement this optimization. We have to mainly ensure that each step inside the while loop can be performed correctly on the GPU. For example, we cannot perform dynamic allocations and deallocations on the GPUs. This is where the frontier reuse analysis that we saw before comes in handy by eliminating the redundant allocations. We also ensure that the loop doesn't have any I/O, graph loading, or graph transformations because these cannot be performed efficiently on the GPU. On identifying an ideal candidate for Kernel Fusion, we move the while loop to a separate CUDA kernel. We also insert prologue and epilogue in the generated CUDA kernel to copy local variables from the main function to the GPU from the CPU. We also insert calls to CUDA memcopy on the host side to assist with these copies. Successfully implementing Kernel Fusion has yet another challenge. Since we're launching a single kernel for the entire loop, we have to launch it with a fixed number of threads. But each step in the loop requires different number of threads depending on the operation they perform. To get around this, we insert an outer loop around each step that multiplexes the fewer threads into a larger number of virtual threads suitable for the task. Graphit semantics also require that each statement inside the loop have a control dependency. We insert appropriate API calls to synchronize the thread hierarchy. Finally, the last piece of the puzzle is the runtime library. This library has efficient implementations of functions for load balancing, vertex subset management, and priority queue management, among others. Even though these are very complicated, we observe that they do not have much variations depending on the schedule. To reduce the complexity of the compiler and the code generator, we move them to a runtime library where the generated code can simply call them. With these techniques combined and the existing CPU infrastructure of the Graphit, G2 is able to generate high-performance code for both CPUs and GPUs from the same representation. Let us now see how G2 generated code compares in terms of performance. For the performance evaluation, we compare the execution time of the code generated from G2 with three other state-of-the-art frameworks, Gunrock, GSwitch, and SubGraph. We run the evaluation on 5 algorithms and 9 datasets. We also run the evaluation on 2 different generations of GPUs, Pascal and Volta, to show portability. The heat map here shows the relative slowdown of each of the framework as compared to the fastest framework in the category. A number 1 in green means the framework performs the fastest in the experiment. A number like 4.28 in red means that the framework performs 4.28x slower than the fastest framework. A gray square means that the framework doesn't support the particular algorithm or graph input. We repeat the experiments on all of the 9 datasets and the 5 algorithms, and here are the results. We also repeat the experiments on the Volta generation GPUs, giving us a total of 90 experiments. G2 performs the fastest on 65 of these experiments. Next, we will also show the number of lines of code required to implement these algorithms in each of the framework. For G2, we include both the lines of code required for the algorithm and the schedule. We can clearly see that G2 can get great performance with far fewer lines of code as compared to the other state-of-the-art frameworks. In our paper, we have a further deep dive analysis where we show the performance improvement from each of the new optimizations that we introduce in G2 separately. With this, I will conclude my talk. I would like to thank the sponsors of this research and would also like to point out that G2 is available open source under the MIT license at the following URL. Thank you.